Okay guys, this is our test 2 review for the intermediate theory class. This test is going to be covering Pythagoras, trigonometry, RMS, peak and instantaneous voltages, vector additions, and what else? Eli the Iceman as well. So let's start off here with our basics. We're going to take a step back. We're going to look at the power equation, and I'm going to use the power equation to show you that the RMS is the DC equivalent. If we look at a sine wave, then we can see that those instantaneous voltages are only there for a brief amount of time and then they're gone. The RMS is usually drawn right about here, and that is our root mean squared. So that is essentially taking the area underneath this waveform right here, and that's giving us the voltage that's actually going to do work. It's the DC equivalent. So if I have 120 volts RMS, that's as if I had a battery that has a voltage of 120 volts. It's the DC equivalent. But hopefully it'll be a little bit more clear by the time we go to the bottom of this page. So let's start off with the DC source here. We're going to put that across a single resistor. Can't get any easier than this. And this resistor, good Lord, what's going on with my drawing today? There we go. Okay, so this resistor right here is 10 ohms, and our voltage is 50 volts DC. So it's always at 50 volts. So, DC source, how much power is this load going to dissipate? So I bet you this question threw you. It threw you because we haven't looked at these equations since the first week. We have three equations for single phase power. Power is equal to voltage times current. Power is equal to I squared times R, and finally power is equal to V squared divided by the resistance. Now any one of these guys is going to give us the power. The one that's going to give us in the least amount of steps is going to be this equation right here, because we have the resistance and we have the voltage, and we're not going to take the time to find the current. You can find the current, it just takes one extra step. So let's use that power is equal to V squared over R. So we have 50 volts. We're going to square that bad boy. Then we're going to put that over 10 ohms. And then if we have 50 squared divided by 10 ohms, so let's see, 50, I don't think I need to use brackets for this guy. 50 squared divided by 10 ohms gives me 250 watts. Okay, so off of this resistor, I've got some heat that's coming off there, and I got 250 watts of heat coming off of that guy. Okay, let's keep going. Number 2. Now suppose the same 10 ohm load is connected to an AC, I love saying this word, sinusoidal power source with a peak voltage of 50 volts. Will the load dissipate the same amount of power, more power, or less power? So pause the video for 2 seconds, think about it. We're now going into a peak voltage, meaning that we're having AC voltage with a peak voltage of 50 volts. So we've got this as our source. We've got a peak voltage of 50 volts peak, and we want to know whether it's going to dissipate the same amount of power, more power, or less power. Well, we know that the peak voltage is only there for a couple of milliseconds, then it's gone, right? It's the RMS that's doing the work. So in order to use any of these equations up here, voltage times current, I squared times R, V squared over R, we need to use the RMS voltage. So first step is to find our RMS voltage, and we're going to do that by taking our 50 volts peak, and we're looking for a lower number, so we're going to multiply it by 0.707, and when we take 50 volts and multiply it by 0.707, or take 70.7% of that, we get a voltage of 35.35. Now that voltage of 35.35 is the voltage that's actually going to do work. Okay, so we got 35.35 volts RMS, and that is the voltage that we can use with any of these equations here. So now, in order to find the power dissipated, again, we're going to take our V squared divided by resistance. So now we got 35.35 volts. We're going to square that. We're going to divide by the same amount of resistance because we haven't changed that. We just changed the voltage that was applied there. So we got 35.35 squared. Let's bring that guy over here. Square that. Divided by 10. And we got 124.96, right? But essentially 125 watts. So that's really interesting because what we've done is we've taken the same circuit here and all we did, I didn't draw out that circuit, but essentially we had an AC source across the same 10 ohm load, right? But the voltage that was there was 35.35 volts RMS because that's the voltage that's actually going to do work. When we put that into our power equation, we see that when we take that same 50 volts, but we use that as a peak voltage, then we end up with half of the wattage there. Okay, so the peak voltage and the RMS are not the same, and we can see that the peak voltage does not give us the DC equivalent. It's going to be the RMS that gives us the DC equivalent, right? Because here we have 50 volts peak giving us only 125 watts, whereas 50 volts DC gave us double that value at 250 watts. Okay, I hope you're following here. Let's keep going. Let's take a look at 3 and 4 and maybe it will make a little bit more sense. So here we've got 100 volts DC, we got 100 ohms, and we need to find the power. So it can't be simpler than this. We're going to do our V squared divided by our resistance. In this case, we're going to do 100 squared divided by 100. We don't need a calculator for this, but let's just show you on here. 100 squared divided by 100. You know the answer already. If I can just get it into the calculator. There we go. So 100 squared divided by 100 gives you 100 watts. Okay? Same voltage, same resistance, same power. Okay, so off of this guy right here, we're getting 100 watts of heat being dissipated. And now number 4, what value of AC RMS voltage is required to have the same power dissipated at the load as that of the DC circuit? Well, hopefully this is where you see what I'm talking about. We need to have the exact same amount of power. We've got the same resistance, so essentially we need the exact same voltage, right? So if we take a look at that equation where we've got power, sorry, a little trippy there, I don't know what's going on with the windows here. Power is equal to V squared divided by R, right? Or if we redraw that, we've got power is equal to V squared over R, right? And we're looking for the voltage, so then we've got V squared is equal to power times resistance, and then we'll have the square root, so the square root of the power times the resistance. Now hopefully you can already see that we need the exact same voltage, right? But let's just put these values in. And again, we've got 100 watts. We're going to multiply that by 100 ohms. And we know that 100 times 100, take the square root, is going to be 100 volts. Okay, so we can see here that we had 100 volts DC giving us 100 watts of power off of that resistor. If we want that same 100 watts of power coming off of that resistor, we need the exact same voltage. We need 100 volts, right? Now, it's not the peak voltage. This here is 100 volts RMS. Okay, the 100 volts is the equivalent of the DC. It provides you with the exact same amount of power as you would from a DC source of equivalent voltage value. Okay, so the RMS is simply the DC equivalent. Number 5, nice easy question here. When AC voltage is being measured with a voltmeter, which value of the AC voltage is going to be indicated? So we know that the peak voltage is the max voltage. The average voltage is that after a DC rectifier. So the value that our meters are always giving us, whether it's current or voltage, are going to be C, the RMS voltage. Excellent. Okay, let's move on, guys. Let's move on to the next page here, number 6. Looks Looks like I dropped down. I missed the answer there, but we know it's not the peak-to-peak voltage either. All right, just eliminate that. So we can move on here. So number 6, guys. Nice, easy question. So remember that my tests are set up so that if you are awake in class and you're taking in what I'm saying each day, then you're going to get 60% on my test. If you're awake and you're actually paying attention, you're going to get an 85 in my class. And then there's going to be some disgusting questions if you want to get that 100%. So this is that one where you're actually awake in class and you've kept track of the fact that how many degrees are there in one complete cycle of alternating voltage. Well, we know that in order to get that AC sine wave, that comes from the 360 degrees rotation of that generator. And if we plot out that generated voltage, then we're going to find a peak voltage, 0 voltage, a peak voltage again, and back to 0, right? This point corresponds to here. Our peak voltage corresponds to here. 180, we're at 0 degrees again. 270, we're back at a peak voltage. And then 360, we are back at the 0 point. So that 360 degrees of rotation of the generator provides us with that 360 electrical degrees on our sine wave. 6 is D. Sine wave has a peak or maximum voltage of 140 volts. What's the voltage at 40 degrees on that waveform? Okay, so for that guy, we've got 140 volts, and we need to find our instantaneous voltage. And we know that our instantaneous voltage is our V peak times the sine of the angle. Okay, why is it the sine of the angle? Let me do a quick little diagram again. Right here, there's that 360 degrees. There's our sine wave. And this is what we were talking about in class, is that if I want to find that voltage right there, that transfers over to our sine wave right there. And that corresponds to a certain degree of rotation. So I can make a right angle triangle there. And if we blow that right angle triangle up, so it's a little bit bigger to see, then this value right here, the radius of the circle, that is our V peak. This value right here translates right over to our sine wave, so that is our instantaneous voltage. This is our opposite of the triangle. This is the hypotenuse. And the ratios of those guys are all based on that angle that's right there. So the relationship out of sine, cos, and tan that looks at the ratio of your instantaneous voltage, knowing your V peak and your angle, is sine. So in order to find your instantaneous voltage, or the opposite, that's our V peak times the sine of the angle. Okay, so let's do that. Over here, our instantaneous voltage is going to be equal to our V peak. So it says a V peak of 140 volts. We got that right there and there. And the angle that we're looking at is 40 degrees. So we're going to multiply that by the sine of 40 degrees. Okay, so let's bring up our calculator. We've got 140 volts times the sine of 40 degrees, close brackets, and that gives us, come on buddy, 89.99 volts instantaneous. So now we're looking for a value that's very close to that, and it looks like E is our best answer there. Okay, so it looks like I just rounded up to 90 volts. Excellent, guys. Okay, let's take a look at number 8 now. A sine wave has a peak voltage of 200 volts. What's the RMS value of voltage? All right, well, let's do that equation in another Ohm's law chart again. So again, we can use the either one of these equations. We can use the fact that we know that our V peak is equal to our VRMS, and we're going to multiply that by 1.414. Or we can use the other equation, which is just the reciprocal of that. Vrms is equal to V peak times 0.707. These guys are the exact same equation. You can see that peak is on the top, RMS is on the bottom. RMS is on the top, peak is on the bottom. These are the reciprocal of each other, and so these are the reciprocal of each other as well. Let me just bring up the calculator and I'll show you what I mean here. If I take 0.707 and I do the reciprocal of that, so if I do 1 divided by 0.707, that's going to give me 1.414. Okay, if I do 1 divided by 1.414, that's going to give me 0.707. Okay, so they're just the reciprocals of each other. Good Lord, that's hard to say. Reciprocals of each other. So this guy and this guy are just the reciprocal of each other, so these are the exact same equation, just in a different form. Man, that was really hard to say. Okay, so a sine wave has a peak value of 200 volts, and we're looking for the RMS. So I'm going to use this guy right here, just because that's how I want to roll today. Vrms is equal to V peak times our 0.707, and so we have a peak voltage of 200 volts. We're going to multiply that by 0.707, and let's see what it gives us for our RMS voltage. Okay, so we got 200, and we're going to multiply that by 0.707. That gives us 141.4 volts. Hey, gorgeous. There it is right there. 8 is C. Beautiful. Okay, nice, easy test, right? This test, if you're in my class, is going to boost your mark. You may have done fairly well in the first test. You're going to rock this second test, get an average of 90 to 100% on this one, because the last test is just killer. Just killer. So you really want to do well on this test. All right, so with this one here, if we're going to find each of our values, and I'm going to give you this chart. This review and the test are just basically a carbon copy of each other, right? They're just different values. So with this one, I've given you basic standard voltages that we're going to see in North America. And we want to find our peak voltage, or I've given you the peak voltage and you wanted to give me the equivalent RMS value. Okay, so again, we know that our RMS voltage is equal to our peak voltage times 0.707. And we know that in order to find our peak voltage, well, that's equal to our RMS voltage. And we're going to multiply that by 1.414. Okay, so why don't we do this side here with our peak voltages first, and I'll put the calculator over on the left-hand side. Okay, so with these guys, can we see our values? There we go, pretty good. So we've got 120 volts as our RMS voltage. We're going to multiply that by 1.414. That gives us 169.68. Okay, if you decided to divide your RMS voltage by 0.707, you're going to get 169.73. Doesn't matter. Either value is good. Okay, let's keep going with 277 so we can finish everything in this column here. So we got 277. We're going to multiply that by 1.414, and we've got 391.68. Okay, you can see how these voltages are slowly increasing here, right? So here, if you had a value of like that was less than 339, then you know that you've had a fat thumb putting into the calculator. Okay, let's do 347. So 347, we're going to multiply that by 1.414, and that gives us 490.66. So if you've been in my class, you've heard my sermon numerous times here. If you're working on 347 volts, that's a disgusting voltage. That's where cellular damage is going to happen. There's going to be, cellular damage over here, but once you have 347 across your hand, it's going to blow your fingers right off. Not essentially blow them off, but it's going to cook your fingers to the point where they're going to have to be amputated. It's not 347 volts that's causing the cellular damage. It's 491 volts peak. Doesn't matter if this is just there for a couple of milliseconds. That is going to boil your blood and absolutely destroy the cellular structure of whatever that current is going through. So, again, if you are working live, you're a donkey. If you have no choice, then and you're working live, then use the appropriate PPE. If you're working for a donkey who continuously makes you work live, then go find somebody else to work for. Right? 347 is a disgusting voltage. You're actually working on 490 volts peak. Okay? Let's keep going. Say some donkey tells you to work on a live 600 volt bus. So what voltage is he actually asking you to work on? Remember that oftentimes our foremen are not the people who know what they're doing. They're just simply people who can push us to get the work done. You know what you're doing, and you know that 600 times 1.414 is an absolutely disgusting voltage of 848.4 volts. So when you're working live on 600 volts should scare the crap out of you. But if this doesn't scare you, then that sure as hell should scare you. 850 volts peak. Okay, here endeth the sermon here, but do not work live. And if some donkey tells you to work live, they're not just asking you to work live on 120 volts, it's 170 volts, right? 347 is actually closer to 500. 600 is a disgusting 848 volts peak. If this does cellular damage, this does a disgusting amount of damage to your body, right? Creates blood clots, causes cellular damage. You got the entry, exit wounds. You don't want to work live. Or if you are going to work live, you're going to use the appropriate PPE. Okay, so let's see if I give you this peak voltage, then let's see if we can find the RMS voltages. And again, we're just going for standard values here, right? So can we fit all this in here? Let's put this in the middle and then we can see what we're doing. Okay, so we got 294.11, so 294, come on, 0.11, and you're going to multiply that by 0.707, and that's going to give us our RMS voltage, and that gives us 207.93. So again, you can give me the 207.93, or you can just round it up to our standard voltage of 208 volts RMS. Okay, if we're doing 339.36, okay, so what do we got? We got 339.36, come on, and then we're going to multiply that again by 0.707 to give us our standard voltage of 239.92, or you can round it up to 240 volts. Okay, so these are our standard voltages in North America: 120, 208, 240, 277, 347. The next one is most likely going to be 480, right? So let's double check with that 678.72. So let's see, we've got 678.72, and we're going to multiply that by 0.707, and that gives us 479.86, or you can round it up to 480. Beautiful. Okay, don't go on cruise control when you're doing this chart here, because I'm going to take some of these columns out. So just be careful that you're not just arbitrarily putting in 480. Do the calculation and just double check. All right, guys. Once you've done this chart, then move on to the next page. Let's go to question number 10. And here I've just given you a diagram that you're going to work from. And I've given you the equation here for your instantaneous voltage. It's the sine of the angle times the peak voltage, right? So don't use the RMS. Always use the peak voltage for your instantaneous voltage. The peak voltage is the radius of the circle, and that will never change. The only thing that's going to change here is the angle. Okay, so let's take a look. If a sine wave has an RMS voltage of 120, what's the instantaneous voltage at each of the following angles? Okay, so we need to find, if we just scroll up here, we need to find our peak voltage first, right? So again, our V peak is going to be equal to our 120 volts RMS times 1.414, and we did that previously and we found that was 169.68. Okay, again, you may have divided by 0.707 and you get a slightly different value of 169.73. Okay, if we draw out our sine wave here, then we can see each of these different angles. So at 30 degrees, that's going to be right there, and we know that's going to be a positive value. At 60 degrees, we know that's going to be a positive value, right? Because anything up here is a positive value. 90 degrees, 135 are all going to be positive values. Okay? But once I get past this 180 degrees, then all the other values are going to be negative. So 225 is going to be a negative, right? 315 is also going to be a negative, and then 360, again, that's just arbitrary. That's going to give us that zero potential as well, right? So let's take a look. Well, now that we've put in all our positives and negatives, because it sucks if you lose a half mark for the wrong polarity of voltage. So at 30 degrees, we need to find our instantaneous voltage, right? So here we're going to do, in this case, this is going to be equal to, let's do the voltage at 30 degrees is going to be equal to the sine of 30 degrees times our 169.68 volts peak. And let's see what that is. Okay, so we've got the sine of 30 degrees. Close my bracket there. Then I'm going to multiply by 169.68. And that gives me 84.84 volts. Okay, so right there I got 84.84 volts. Excellent. Okay, again, before you start this test, make sure you're in degrees and not in radians. Because it sucks when you're in radians and then you're getting all the voltage values as the wrong value. Okay, so that is a positive 84.84. Okay, then we're looking at the voltage at 60 degrees, so we're going to do the sine of 60 degrees. We're going to multiply that again by the same peak voltage. Okay, so let's clear this out. We've got the sine of 60, close brackets. Then we're going to multiply that by 169.68. And that gives us 146.95. Okay, so this value right here is 146.95 volts. Okay, we can see that it's slowly climbing. At 90 degrees, we don't need to do any, well, we'll do the calculation just to show, right? But we know that at 90 degrees, we're going to get the peak voltage. Right? We know that this voltage right here is 169.68. Let's put it into the calculator, but you'll see that the sine of 90 is equal to 1. 1 times 169.68 is 169.68. We always get our peak voltage at 90 degrees. Okay, then at 135, then the voltage is dissipating, right? So let's find our voltage at 135. So we got voltage at 135 will be the sine of 135 degrees. And again, multiplying by that 169.68 volts peak. Okay, so let's see what we get there. So we've got Let's clear this out. The sine of 135. And we're going to multiply that by 169.68. Now, if we look at 135, that's 90 plus 45 degrees, right? So lo and behold, it gives us 119.98 or 120 volts, right? So that gives us our RMS. Every 45 degrees of rotation, we're going to get our RMS voltage. So to be specific, 119.98, but we know that's the same as 120. Okay, and again, that was a positive value. Excellent. Okay, let's keep going. At 225, so here we had 119.98, right? For our voltage value there. And now we're going to do 225 and 315 and then 360. So let me get rid of this guy. You can see that the voltage is slowly climbing to the peak voltage, then decreasing again, right? So as these angles increase, the voltage goes to the peak value and then starts to subside again. Okay, so just keep track of your values. Always use your peak voltage for any of these calculations and make sure you're in degrees rather than radians. Okay, so here our voltage at 225 degrees is again equal to the sine of that angle, so 225 degrees, and then we're going to multiply by our 169.68. That's the radius of that circle. That is never changing. That's our constant. And so sine of 225 multiplied by 169.68. And again, that gives us minus, right? So we already kept that in mind, right? So it's going to give us negative 119.98. So that gives us our negative voltage RMS. So that must be 45 degrees of rotation again, right? And if we take the 180 plus the 45, that gives us 225 degrees. Okay, we already knew it was going to be a negative value as well. Okay, let's take a look at 315. Well, the voltage at 315 degrees, I can see a trend, is going to be equal to the sine of 315 degrees multiplied by our same radius or same peak voltage. So again, let's clear this out, but we know what the answer is going to be. We have the sine of 315, let's close those brackets, times 169.68, and that gives us again negative 119.98. Come on, guys. Okay, we knew it was going to be a negative value, so we already put that negative in there. And we can see that it's going to be our RMS voltage again. Every 45 degrees of rotation, we're always getting our RMS voltage. Here we have 315, but if we take 270 plus another 45, that gives us 315. And that gives us our RMS voltage once again. Okay, just for giggles, let's do this voltage at 360 degrees, but we know what that value is going to be as well. So we do the sine of 360 degrees multiplied by our peak voltage, always the peak voltage here for instantaneous voltages. So we've got the sine of 360 and we're going to multiply that by our peak voltage. And again, that gives us nothing. Because if we take, again, if we just take the sine of 360 degrees, well, that gives us nothing, right? So at 360 degrees, that is the same as 0 degrees, and we get 0 volts being induced. So you can see now that if you know those base equations that we covered in class, you're going to rock this test, right? This was one equation, and we found 1, 2, 3, 4, 5, 6, 7 different values, right? Using the same equation, but I'm looking for the fact that you can recognize it's a positive voltage or a negative voltage here. And you can see that the RMS is coming in a number of times. Okay, let's keep going on. Number 11. Now, number 11 is again a power equation here. So we've got the resistance of the heater at 60 ohms. So let's draw that guy in. Okay, we have a maximum or peak voltage of 169.68. So that's our peak voltage. And we're finding our instantaneous voltage 30 degrees after the voltage is 0 and increasing in a positive direction. Okay, lots of words. We're looking for the instantaneous voltage at 30 degrees. We know that from the previous question, our instantaneous voltage is our V peak times the sine of whatever angle we're looking at. Our V peak here is 169.68. We're going to multiply by the sine of 30 degrees. I believe we did, whoa, easy now. I believe we did that on a previous question. Let's look at that one at 30 degrees. We found that right here. That was 84.84 volts. Okay, now we're looking for the RMS value of current. Okay, so at that point, we can't use that peak voltage, right? Any Ohm's law or Watt's law is going to use the RMS values. So for 169.68, we know now that that's equal to a voltage of 120 volts RMS. Okay, and that's the voltage we're going to use when we're finding the RMS value of current. So RMS value is used for Ohm's law and Watt's law. The peak voltage is only there for a brief instant. So we're always going to use the RMS for these guys when we're looking for RMS or our power equation. So here we know that our voltage here that's impressed across this is 120 volts RMS, and we're looking for the RMS current. Okay, well that is just basically Ohm's law, right? We have 120 volts. Let's see if we can find everything. 120 volts RMS impressed across 60 ohms. And obviously the current is going to be 2 amps RMS. Okay? Nice and easy. Don't overcomplicate it. What's the power in watts used by the heater unit? Again, Ohm's law and Watt's law, they're all using the root mean squared value. So the power now, if we have 2 amps and we've got 120 volts, we know that power is equal to voltage times current. The voltage that we're using is the RMS voltage. The current that we're using is the RMS voltage. And we can see here that our wattage is going to be 240 watts dissipated across that heater. Alright guys, next one is the instantaneous value of current in amps at 270 degrees. And does the current have a positive or negative polarity? So, if we draw out our sine wave, this question is primarily just so that you know what I didn't clue into at the end of trade school. I always thought that current was always a constant value. I thought the current never changed. Like if the value was 5 amps, then it was always at 5 amps. Or if the value was 2 amps, it was always at 2 amps. But that's not true at all. As we have more voltage, we get more current. So our current waveform looks like this as well. It's a sine wave as well. So as we get more pressure, we get more flow, right? There's our current, there's our voltage. So current is not a straight line. Current is a sine wave, just like the voltage waveform. So now we want to find the current at 270 degrees. Well, it's clear there that at 270 degrees, we're going to get our peak voltage and we're going to get our peak current. So we can use the exact same equation in order to find our peak current now. Right? So if we had this equation here where we had our V peak was equal to VRMS times 1.414, right? We could also find our instantaneous voltage, right? So we could also find our instantaneous voltage as well by taking V instantaneous, and we said that was equal to our V peak times the sine of the angle. So this one doesn't really help us, but the other equation does help us if we want to find our instantaneous current, right? So instead of having instantaneous voltage, we could do instantaneous current and have the exact same relationship, right? That would be our peak current times the sine of the angle. Now, how do we find that peak current? Well, in order to find that peak current, that would be our RMS value, and we'll multiply it by 1.414, right? So we've got 2 amps as our RMS value, multiply that by 1.414, and that gives us 2.828 amps peak. Right? So we can clearly see that at 270 degrees, we're going to get our peak voltage. Not only are we going to get our peak voltage, we're going to get the negative peak voltage. So we know that our instantaneous voltage at 270 degrees is going to be equal to our 2.828 amps. And not only is it our 2.828, it's going to be negative 2.828 amps. Okay, so let's just find that by punching it into this equation here. Instantaneous voltage is supposed to be our peak times the sine of the angle. So we've got our peak voltage here, peak current of 2.828. And we're going to multiply it by the sine of 270. And that gives us negative 2.828 amps. Okay, so doing a diagram really helps to find your answers as you go through. Easy, huh? What happened there? Okay, so doing this diagram right here is going to show you exactly what's going on and help you to find the answer before you actually pump it into the calculator there. All right, guys, let's keep moving on. The next one is number 12. We're looking at offset heights of 8 inches, but different degrees. We've got 10 degrees on this guy and 45 degrees on this guy. So let's do 2 different diagrams here for question number 12. The first one is going to be like this, where we've got 10 degrees. Easy, come on. 10 degrees is our angle. And we've got 8 inches for the offset, and we want to know the hypotenuse. And here we've got a 45-degree triangle. And we know that, well, I guess I should draw this out the same height, right? Otherwise, that's a bit misleading. Again, this is 8 inches, and this angle is 45 degrees. Okay? So hopefully you can remember that the relationship for these guys in that this is the opposite, and we're looking for the hypotenuse, and we also know the angle, is that we need to use sine, right? So we know that the sine ratio is the opposite over the hypotenuse. So if we're looking for the hypotenuse, it's going to be the opposite divided by the sine of the angle. So here we're going to have, let's put this here. So in this case, our opposite is 8 inches. We're going to divide it by the sine of 10 degrees, and we'll see what the distance is across this hypotenuse here. Okay, so what have we got? Let's move this over here. We've got 8 divided by the sine of 10 degrees. And that gives us 46.07 inches. Okay, if we want to find the hypotenuse here, then again we're going to use the exact same equation. We're going to use the opposite divided by the sine of the angle. In that case, again, our opposite is 8, but our angle has now changed to 45 degrees, and the distance on the hypotenuse is going to be a lot less. Right? So again, move this bad boy over here so we can see what we're doing. We do 8 divided by the sine of 45 degrees, and that gives us 11.31 inches. Excellent. Okay, so we can see that by changing the angle, it changes the ratio of everything in those triangles. Alright guys, let's move on to number 13. Starting with a 10-foot piece of conduit. So we know that 10 feet is equal to 12 inches times 10. That gives us 120 inches to start with. We're going to do a saddle here, and it's going to be bent at 30 degrees with an offset height of 6 inches. And what's the new total length once the pipe is bent? So we need to find the distance between here and here, and that's after our bends are put into the pipe. So the pipe is going to shrink significantly once we put in those two offsets. So we know that we need to draw out a triangle like this with an angle of 30 degrees. These guys are meeting at right angles, and the offset height right here is 6 inches. Okay, so we know that from pipe bending that our multiplier for 30 degrees is 2, but we're wanting to find our hypotenuse, which we're going to find is probably 12, right? 2 times 6 is 12. And then we need the adjacent, because the shrink, the amount that the pipe is going to shrink per offset, and by offset I mean that every time that we do an offset like this, we're going to lose a certain amount of distance there on our pipe, and the difference is our hypotenuse minus the adjacent value. So let's find those two values. So we've got the angle, we've got the opposite here, and we're trying to find the hypotenuse, so let's do that first. We'll do that using sine. So we know that is our opposite over our hypotenuse. So we can find our hypotenuse then by taking our opposite of 6 inches and dividing it by the sine of 30 degrees. Now we know that that's going to be 12, but let's just pump that into the calculator just to make sure. We've got 6 divided by the sine of 30 degrees. And that gives us 12. There we go. Everything's good with the universe. We have 12 inches for this bad boy right here. And then we need to find the adjacent. Again, we can find the adjacent using Pythagoras. 12 squared minus 6 squared. Square root will give us our adjacent. Or we can make use of the cos relationship. So let's do that. Cos of that angle is the adjacent over the hypotenuse. So in order to find the adjacent, we're now going to take the cos of 30 degrees and multiply by the hypotenuse, which you just found to be 12. Okay, so we have the cos of 30 degrees, and we're going to multiply that by 12. That gives us 10.39. Okay, we're going to pump each of those values into this equation here. Our hypotenuse was 12. What just happened? There we go. Okay, it was a glitch in the matrix. So 12 minus our adjacent of 10.39. That gives us 1.61. So we're going to lose 1.61 inches for each offset. Okay, when we did this saddle, we did one offset, then we did the exact same offset. So 2 times that value, so total loss is going to be equal to 2 times 1.61. Okay, so 2 times 1.61 gives us 3.22. And finally, our new length, let's do a different color so we can see what we're doing here. So our new length is going to be equal to the 120 that we started with minus the 3.22 inches that we just lost. And our new length is going to be 120 minus the 3.22. Come on, buddy. 120 minus 3.22 to be precise. That gives us 116.78. So our new length of pipe is 116.78 inches. And again, if you've got all kinds of calculations on the page, then do me a favor and make my life easier and just circle the answer there. All right, guys. Doing well. Let's move on to number 14. So number 14 is a vector addition. What I'm going to do is I'm going to stop here so that I can put this video on 2 different playlists. On this play for the review and the other playlist for vector additions as well. So we'll stop the video right here, continue on in the playlist, and you'll find this vector addition. And then I'll finish off each of the vector additions there. I can put them into other playlists, and then we'll come back and we'll do Eli the Iceman at the end as well. But just stop here and continue on the playlist, and you'll find question number 14.